Jnanam paramam dheyam. Knowledge is supreme.
Clear? Kind of summarizing whatever you have seen in the last lectures. So, getting with this, all these definition in place, what are the postulates of quantum mechanics? So, this I have been repeating many times. You have a quantum mechanical system with some dynamics, and you formally say all the information about the state of the system is going to be contained in this psi. So, that is the first postulate. You say that the system is prepared in the state psi. So, all the physical observables, some of the simple ones which we are familiar, position, momentum, angular momentum, energy. In quantum mechanics, we associate operator to every observable. So, that is one of the. So, and this also we saw that all the adjoint operators should be equal to the operator, which is what we call it as the Hermitian condition. Eigenvalues of the Hermitian operator have to be real, or equivalently any expectation value of any operator, if it is real, then that operator corresponds to the observables. Yes, that is the first requirement. All the operators in quantum mechanics which corresponds to observables must satisfy linear. All the operators, in fact, whether it corresponds to observables or not, we will take them to be linear operator. Okay. There are some operators which are antilinear operators also, but that is something you need to think. Okay. What is an antilinear property, you know? At least for the observables which we are going to study is linear. Let me answer this question. So, we had this A operator on C times psi. We wrote this as C times A operator on psi. So, this is the linear operator. If it is antilinear operator, you have to complex conjugate the coefficients. Okay. So, antilinear operator, let me call it as O, satisfies some point. If we have time, we will talk about this. There is a time reversal operator which has to satisfy this property. We will come to it. So, at least for all the practical purpose right now, what we are going to take is the observables which we are studying, like momentum, energy, all these things satisfy the linearity property. So, you are looking at linear operators. There are some more subtleties here, that all your this antilinear operator, which is a time reversal, if you do 2 time reversal, it is identity. So, it is only defined for discrete operation, but whereas you for continuous operation like translation or rotations, the operator has to be a linear operator. So, we have seen this also, an eigenvalue equation. I defined it for any operator, for example, A operator. This lambda I is called as the eigenvalue, and phi i's are the eigenstates of this operator A. You have to get used to this notation. Eigenvalue equation means which is an eigenvalue, which is an eigenfunction, and the eigenfunction will be an eigenfunction with respect to one operator. Okay. Sometimes there will be another operator which will also have the same eigenfunction, then this is the same eigenfunction for both the operators. So, all these possibilities exist. It can be a different eigenfunction or it can be the same eigenfunction. Okay. So, this is an eigenvalue equation, and we also need the linear operators to satisfy this property. This also I said, whenever you take the initial state, this A psi will give you a new state. You can replace it as psi with A dagger, and with psi, and then that's an inner product property which should have the star. And then we also said that for observables whose expectation values have to be real, you have to have this property will force that A is equal to A dagger. So I asked you to find out d by dx expectation value on a state psi, right? And you have done this in the wave function formalism. Take the particle in the ground state or first excited state, and this expectation value can be taken to be, if it is ground state, this will be integral over dx 0 to L psi 1 of x d by dx psi 1 of x, right. Formally you can do this for not even for a particle in a box. You can take in general a free particle. You can take this from minus infinity to plus infinity and say that the wave function should vanish. So well defined, it belongs to L2 of minus infinity to plus infinity, the wave function should vanish at plus or minus infinity, and you can work this out. Please do this and you will see that this will be same as negative of integral. So this is a star negative of integral dx minus infinity to plus infinity. Okay, so you can have a d by dx dagger psi 1 of x psi 1. So you can show that the expectation value of d by dx is same as negative of expectation value of d by dx dagger. What does that mean? If expectation value is in general complex, a plus ib should be same as, so let's write this to be a plus ib. Okay, this one will tell me it is a minus ib with a negative sign. So a equal to minus a means a is 0. So it's only b which is survived. B is only purely imaginary. So if you take the expectation value of a del by del x operator, you can show that that expectation value is purely imaginary. So they don't correspond to observables. Observables should have real eigenvalues, and the expectation values which gives by Ehrenfest's theorem related to your classical results, they have to be real. So the only way you can make it real is you put a IH cross here, then this will become a minus IH cross. Sorry, this is minus IH cross, so this will become a plus IH cross. You will also come to why it is minus IH cross del by del x for the momentum operator. I don't think you know how the derivation goes to show that the linear momentum as an operator has to be minus IH cross del by del x. So this plus and this minus will give you the same. Okay, so then there is no minus sign here. I will play around with a plus ib, sorry, a minus ib, right, because there is a dagger here, which means these two will cancel, only a will. So that's why the expectation values of observables have to be real. Just as a toy example I am telling how to do it for a d by dx operator. Fine. Oops. So for all observables which we study, the eigenvalues have to be real. So those operators are called self-adjoint operators, which are denoted by a equal to a dagger. They are also called Hermitian operators. There is a slight subtle difference between Hermitian and self-adjoint, but for all practical purpose in this course, we can call Hermitian as self-adjoint operators. Okay. We will not get into that. There is a formal way in which you have to look at domain of an operator and so on. We will not get into it. I introduced you the Fourier transform, which kind of told that if you have a square summable sequence and a finite dimensional or a countable infinite dimensional, all these things we have done. But when we did the Fourier transform by taking K to be a continuum, there also it is actually a uncountable continuum linear vector space, right. So, the set of Kns which we have, which corresponds to the phi n of x for periodic functions, we could have a K which is similar to what we wrote as e to the I k x as the basis functions, right. We do this. So, this one has a discretized index. So, Kns is a set of allowed wave vectors, and for that we have this corresponding wave functions phi n of x, remember, recall that, right. But then we also went into a wave packet where we used the basis functions as e to the I k x and k was a continuum. So, with periodicity we showed Kn to be like 2n pi by r. Here this K is there is no condition, K will actually go as K plus delta K, so on it is, then dk is very small. So, this is a continuum. So, this vector space is countable, but it can be infinite dimensional, right, like particle in a box, stationary states, the phi n of x which you write, n can go up to, there is no cutoff, it is infinite dimensional, but countable in the sense that it is a summed up series, right. But if you look at a free particle, these basis functions are also for a linear vector space, but here there is a continuum called such a linear vector space to be an uncountable linear vector space. Slowly taking you into abstract notation by showing you some simple examples, I hope you appreciate. So, this is where we get into the uncountable continuum linear vector space. Some of the things which we can start doing is we can introduce basis states in the position space, okay. So, x is a continuum, it goes from minus infinity to plus infinity like the K. So, I will formally, following the Dirac notation, write the basis states in position space by a Ktex. Allowed? How will you write completeness and orthonormality in this continuum vector space? Exactly like what you did in the discrete. You have to only replace wherever summation over n was there by an integral over dx, because x is the variable. So, we have in the continuum linear vector space uncountable, there is an outer product summed up over all the positions, but the positions are continuum. So, there is no point in putting a summation, you have to put an integration. Suppose you are in some kind of a checker box that the ball will only fall at L, 2L, 3L, then this position will become discretized. Then the integration can be removed and you can put a summation. But I am trying to say that the particle can be anywhere from minus infinity to plus infinity. So, this is a well defined position basis for that, and following our completeness and orthogonality for a continuum vector space, we can define the completeness relation to be this and orthogonality to be the Dirac delta function. Confining myself to one dimension. What will happen if I go to two dimension? There will be two integrations dx dy. Each state which I have written, I could write x comma y outer product, and we can do this. What happens here? It will be a Dirac delta function in two dimensions. I am taking you to this through this so that slowly we will see what exactly is wave function, which you all studied, which we were doing. You could write a wave function, or you can define the Dirac formalism of a ket and ket in the position basis, ket in the abstract basis, and we can see how to get wave functions which you studied using this position basis. So that's why I am trying to stress the position basis. Any arbitrary state you can expand in any basis, that's what I was trying to tell you. It is not required that you have to expand it in momentum basis alone. You can expand it in position basis, you can expand in energy basis. Like all your particle in a box, when you expand it a superposed wave, it is taking the stationary states which are energy basis, right? The phi n's Hamiltonian operator on them gave you a specific energy, nth excited state energy. So that's an energy basis. So you can here I can do the psi as a position basis. Why not? Any basis is good enough. So if I do that, I can just insert the identity operator and write this. What will we call this as? This inner product. It is the probability amplitude for an arbitrary state psi to be in position specific x. This probability amplitude in the position basis is what you all study as wave functions. What you have been seeing as wave functions are nothing but the probability amplitude for an arbitrary state psi to be in the position x is given by this inner product, and that is what we call it as a wave function. So whenever you do wave functions, there you can go and replace it as an inner product, and we can try to see whether everything is consistent. So this is what we call it as a wave function. So what is expectation value? This also I said, for a system prepared in state psi, the expectation value of some operator x, for example, let us take this to be the position operator. In quantum mechanics, in the Dirac notation, I would have, if the state is in psi, then this is what I would have written. But equivalently, I can insert this parenthesis, which is nothing but a identity operator, which is what I have done here. And once I put this identity operator, you can see that this psi with this x is the complex conjugate of your wave function, and then the x operator on the x basis will give you an eigenvalue equation. The x operator operates on the state x will give you an eigenvalue x times x. So operator is gone, you got an eigenvalue, and then what are we left with? The psi inner product with x. What is that? So we are going to define an operator x on the position basis. So let us take some x naught specifically. If I say it is the position basis, the position operator on x naught state will give you, suppose I take a state with some momentum and I operate a momentum operator, I am supposed to pull out that number of that state, right. So this state is at a, let us say the state is at x naught and I have a position operator, it hits that state. What? You will get a position eigenvalue which will give information about that state and x naught. So this is an eigenvalue equation for the position operator with eigenvalue x naught and ket x naught is what I call it as a eigenfunction. So the position basis means they are eigenstates of the position operator. Okay. So if I use this, then whatever I wrote psi x operator psi, formally I could have a psi and then integral over dx x x, and then I have an x operator on psi. So this integral over dx I can take it out, not a problem. This will be psi with x, and you have an x operator operating on x, that will give you eigenvalue x. You are still puzzled? I wrote x naught earlier. Yeah, but all the observables, the eigenvalues are real. All your position operators are all, it's an adjoint operator. If you want, you can take, it's the x star you can write, but x star is same as x for all observables. The eigenvalues are always real, so you don't need to write star. If it is some other operator which has no correspondence with observables, then technically I have to put a star there. Otherwise, I don't need. Agreed? So here I am trying to say that in x naught with x operator is, formally you would have written x naught with x naught eigenvalue as a star, but since this is a observable, lambda equal to lambda star, so this will be, the eigenvalue will be real. So we don't need to put a star. It's okay. So then what else is left? That comes out with psi. So this piece is what we called it as wave function psi of x. And if we call this as psi of x, this one has to be called as psi star of x. And x integrated over dx. You get back your earlier quantum mechanics where you did in the wave function formalism, but here I had the Dirac notation, but I inserted a position basis completeness identity operator in position basis and then went to the familiar wave functions. It is, see, this notation is so neat that you can go back and forth between wave function and the state vector formalism. I don't know, this angular bracket is so really very elegant. And now we all universally follow it. So I want you to appreciate that you can also start using this by inserting unit operator in between any time for convenience. Like if I am looking at position operator, I will put a unit operator in the position basis. But if I am looking at momentum operator, I could do, unit operator can be in any basis. I can also put a momentum basis, right? You start seeing that, start doing that momentum basis, and the corresponding momentum operator on the momentum basis will give you the appropriate eigenvalues. And to go from position basis to the momentum basis, what will you do? Again you do this inserting unit operator, right? Let me formally write that. You have a position basis which I can write dp, pp, this is identity operator operating on x, nothing wrong. So if I take x, then this is dp, state p, and then this inner product of p with x. What is this inner product one has to find? And we will do this at some point and we will show that it is like e to the I px by h cross. So this will turn out to be e to the I px by h cross. We will prove this, okay. So it's in some sense going from one basis to another, between momentum basis and the energy base, momentum basis and the position basis, the Fourier transform shows up. But I have introduced for you that there is a unit operator in the continuum linear vector space, uncountable linear vector space, which is, this is the completeness condition, and the corresponding orthogonality condition in momentum space will be p prime. If you are in one dimensions, you have px prime, then this will be a delta function of px minus px prime. So you need to remember that when you are in uncountable continuum linear vector space, you will have the Dirac delta function for orthonormality. We did this in the function space. You go back and rewrite. So function space is similar to what you do with the wave functions. You will see all of them will be visible there. So for a system in an abstract state psi, we can work out this expectation value for a position operator either in this wave function formalism or here, and both are equivalent. This is exactly equal to evaluating psi star x, x psi of x, which you have done in your first year course. So once we have operators and expectation values, we would also like to see what is the uncertainty in their evaluation. It's nothing similar to your standard deviation, right? So how do you define that? You define uncertainty in the position is find the expectation value of the square of the position operator, subtract out the expectation value of x and then take the square, like standard deviation. Standard deviation you have to do it on the expectation values. Yeah, so you have done, right, with a square root. Thank you. Yeah, so there should be a square root, or you can write square delta x squared. Okay, I want to spend some time on this measurement issues. If you want to measure position, if you want to measure energy, given a state to you, how do you know what is the energy of that state? For example, if it is a stationary state, you operate a Hamiltonian operator which is equivalent to finding an expectation value of your Hamiltonian. By Ehrenfest's theorem, it should be equal to the energy or average energy. But if the state is an eigenstate, then it will actually give you the exact energy, right? So Hamiltonian, suppose it's operating on some psi n, is En times psi n, and your state is in this psi n. This is expectation value of psi n. What will this be? It gives you En. So if a state prepared is in a perfect eigenstate, if you try to measure the energy of that state or try to find the average energy of the system prepared in that state, both will be same, giving you some energy eigenvalue. But what exactly you are doing in expectation values for a superposed state? Suppose I have a superposition Cn on psi n. What exactly are you doing here? When you try to do a measurement, what happens? System collapses to one particular, which state we don't know, but any of these. Suppose I tell you that the system has these stationary states possible, I know some n value it will collapse to, right? But how will I determine Cn? You take the same identically prepared system, let's take 100 of them. In each of that identically prepared system, simultaneously you do the measurement and find, suppose take this 10 rows, each row is doing the measurement on an identical system. You say E1 as the energy, somebody says E2 as energy, and so on. So if it is infinite, I can find out how many of you got E1, how many of you got E2, and I can take the average. So that mod Cn squared is the probability of finding energy value as En. Okay. Since we always take it to be normalized, the state psi is normalized. What does it mean? Equal to 1. So this is what, for a specific energy, when you have infinitely identically prepared system and you try to do a simultaneous measurement, each system you will have different energies. somebody will get something. But if you take that and see, tabulate how many of these systems got E1, how many, then you can actually find the mod Cn squared. Okay. So this is what we get the information from a state vector, and we find this mod Cn squared by doing this on an identically prepared system. So measurement when we do, when I take the state, one person when he does the measurement, suppose that table he is doing a measurement, he doesn't know whether he will get E1 or E2 or E3 or something, but it will definitely be in that set. If the system has stationary states with energy E1, E2, E3, when he does the measurement, he will not get 1.1 times E1, okay, or he will not, he will get E1 or E2. You can't get something intermediate in between. That he will not measure. He will measure only one of the stationary state energy eigenvalue. Which stationary state energy eigenvalue he will measure? Nobody knows. Nobody knows. He will either get E1, E2 or E3 and so on, but he will not get somewhere in between. You will not get something like E1 plus 0.1 or something. He won't get that. That is for sure. But which one he will get, he himself will not know. That is where the probability gets into the picture. That is very intrinsic and nothing you can do. So measurement by an observer on a state psi will make it to go into one of the stationary state. So this is what we call it as a collapse of this wave function, and you will have an energy which you cannot predict what it will be, but it will be one amongst that set of stationary eigenvalues. So if you take for measurement, take n identically prepared system. Psi is the state of the system. Before we measure the energy of the system, we can only say it will be one of the set of allowed energy eigenvalue. We cannot say which energy eigenvalue. So once you do a measurement, the state collapses to one of the energy eigenvalues, energy eigenstates. So when you do this measurement, so when I do this Hamiltonian operator on psi, which is Hamiltonian operator on summation over n Cn psi n, what I will get is, I will get some specific Em state, so psi m state. This is all he will get. And after this, when he starts measuring Hamiltonian on this, it will give you energy Em on psi m. It will remain in that stationary state after that. An observer who is trying to measure in an arbitrary state will see that the state psi will collapse to some stationary state. Which stationary state he doesn't know when he is doing the measurement. It's not a specific M. One of the set of this. After he has, it will remain in that state throughout. It will remain as psi m. Again, if he does the measurement on it, he will not get a new energy. He will get the same energy. Is that clear? So the measurement on a system leads to a collapse of psi to psi m, a specific eigenstate, and it will have an energy which is measured by him. After that, if he again repeats to measure the energy again, it will remain in that state. It will not. Then he can have a predictive answer. Takes a superposed state and does a measurement. Till he measures, he doesn't know what is the energy. Even before measurement, he cannot guess. But he gets it to collapse to a specific stationary state, which is an energy eigenstate. After it does collapse, if he tries to measure again and again, he will get the same energy value. So as long as the system is undisturbed. What do I mean by that? I cannot make the stationary state to undergo some other transformation. If I do that, then it may again go into a superposed state. As long as I don't disturb the system, I keep it. After collapse, it will remain in that collapse state, which is one of the eigenstates of that operator. Okay, so let me stop here.